Kinematics Equation 3. We can combine the two equations we've been working with, Kinematics Equations 1 and 2, to get Kinematics Equation 3. In doing so, we can eliminate time from the equation. Just solve Kinematics Equation 1 for time, then substitute it into Kinematics Equation 2. Finally, solve for v squared, final velocity. The algebra is shown on the next slide, but it is great to do on your own if you would like to practice solving systems of linear equations. The result is eliminating time. It is Kinematics Equation 3. It is final velocity squared equals initial velocity squared plus 2a change in x. This equation is very handy for situations where we're not given information about time or asked about it at all. Once again, this equation includes x subscripts here, here, and here, and x is here, for the vector quantities. Only acceleration and velocity in the x dimension will affect an object's position in the x dimension. So here's the algebra for combining the first and second kinematics equation. You can read through it. This is one way to do it. I tend to solve it a different way. So what I'm going to do, just for fun, is I'm going to erase all this. Well, actually, first let me just walk you through it, and then I'll erase it and solve it the way I normally solve it. So here's the first kinematics equation, solve it for time. Plug that value for t in here and here in the second kinematics equation. Don't forget, this t is squared. So when you put these in, you see that this term is going to become pretty big because we have squared, so it's going to get a little confusing. To get rid of that denominator, they go ahead and they multiplied both sides, but they multiplied every term by 2ax, 2a. The x just shows that it's in the same dimension as the velocities. Then they combine like terms, rearrange to solve for v squared, and we get the third kinematics equation. V squared equals v naught squared plus 2a delta x, change in x. Here's how I solve this. All right, let's start from scratch. We have v equals v naught plus at, and I'm going to solve that for time. So v naught goes to the other side, v minus v naught, divide by a. All right, now we have x equals x naught plus v naught t plus 1/2 at squared. I'm going to take this value for t and plug it in here and here. So we have x equals x naught plus v naught. Instead of t, I'm going to put in v minus v naught over a plus 1/2 a, and then t, v minus v naught over a. Remember, I'm getting that from over here. And then that is squared. So this squared is a bunch of algebra. So I'm going to do that over here real quick. So we have v minus v naught over a times v minus v naught over a. So we're going to do FOIL on top, right? First, outer, inner, last. V times v is v squared minus v naught minus v times v naught plus v naught squared over a squared. Now we can combine those, right? So this becomes v squared minus 2v times v naught plus v naught squared over a squared. So now I'm going to go back here. I'm going to put that in here. So we have, okay, maybe I'll multiply this out as well. So v naught times v minus v naught times v naught, so that's v naught squared. That's all over a, plus we have 1/2 times a times this result. That's v squared minus 2v v naught plus v naught squared over a squared. Okay, so this a cancels with one of those a's. And now look, they both are over a. So I can combine the numerators. They have a common denominator. So these two terms here, this 2, oh, actually, this 2 ends up down here. So we're going to have to multiply top and bottom by 2 so that they actually do have a common denominator. So that's going to add 2 times this whole numerator. So we have 2 v naught v minus 2 v naught squared over 2a All right, so I already put the 2 down there, so we got rid of that 1/2. Now we have this, we're just going to be adding on all of these as well, because they do have that common denominator. So we have plus v squared minus 2v v naught plus v naught squared. And this is all over 2a. I'm actually going to rewrite it in the middle. Now we combine like terms. So we have x equals x naught plus, okay, we have 2v naught v here, and we have negative 2v naught v, right? Doesn't matter what order they're multiplied in. So that cancels with that. We have negative, so we have just one v squared. So I'm going to put that here, v squared. Got it. Negative 2v naught squared plus v naught squared gives us 1 negative v naught squared. So that's minus v naught squared over 2a. Okay, so we're solving this equation, remember, for v squared. So I'm going to subtract, I'm going to flip this whole equation around. So it's v squared minus v naught squared over 2a. I'm going to subtract that x naught to the other side. So that becomes x minus x naught. I'm going to multiply both sides by 2a so that it cancels over here. And I'm going to go up here. So now we have v squared minus v naught squared equals 2a times x minus x naught, running out of space. Finally, I'm going to add v naught squared to both sides, plus 2a x minus x naught. Whew! Done. This is the third kinematics equation. This is how I solve it in my classroom. There are obviously different ways to go about it. Just follow the rules of algebra and it will work out. But this is how we have the third kinematics equation, by eliminating time in solving the system of linear equations. We will not be trying to graph this equation. We're only going to use it algebraically. However, in any kinematics problem, this equation will also hold true. An object accelerates from rest with a constant acceleration of 7.5 meters per second squared. How fast will it be traveling after it goes 21 meters? All right, so our givens. We have our initial position of 0, our initial velocity of 0, because it starts from rest, our final position of 21 meters, our acceleration of 7.5 meters per second squared. We are solving for velocity. As you can see, time is nowhere to be found in this whole problem. That's your hint that it's kinematics equation 3. So the first term goes away since v naught is 0. X naught is also 0, so that goes away. V squared equals 2ax. Take the square root of both sides, and we get the square root of 2ax. Plug in your numbers. Your velocity is 17.8 meters per second. An object accelerates from rest to a speed of 24 meters per second over a distance of 56 meters. What acceleration did it experience? Here are our givens. Our initial position is 0. Our initial velocity is 0. Our final position is 56 meters. Our final velocity is 24 meters per second. So, no time. Let's go to kinematics equation 3 and solve for a. So first we eliminate that term and that term because they're both 0. So we get v squared equals 2ax. We are solving for a, so therefore we're going to divide by 2x. So that goes to the other side. A equals v squared over 2x. Plug in your givens and you get 5 meters per second squared. An object experiences an acceleration of 6.8 meters per second squared. As a result, it accelerates from rest to 24 meters per second. What distance did it travel during that acceleration? Here are our givens. Let's assume we start at the origin, 0 meters. Our initial velocity, also 0 meters per second. Acceleration is 6.8, velocity is 24. No time. We're not asked about time. We're not given any time information. We are using kinematics equation 3. This term is 0. That term is also 0. We're going to solve for x. So we get v squared equals 2ax. Divide both sides by 2a. Plug in our givens. Don't forget to square that velocity and we get 42.4 meters.